development, or how I have figured out that biophotonics in some way have developed, and which things that we are able to solve today, and what questions also arise or raised in this area. So if we start, I have unfortunately perhaps too many slides, but we can see if we can live with that. Biophotonics is quite often regarded as when photons interact with something, and as a quantum unit. So everything that goes under that definition is probably quite often known as biophotonics. A large development has been around lasers, and you have been very successful, I would say, here in Riga or in Latvia of developing lasers and laser technology used in biophotonics. And the stakeholders, those who are using this, of course, is the medicine or medical imaging. And I think imaging is one of the words that will appear during the speech very much. We started quite often with looking at very small, tiny, or pencil-like introduction of light. And when I talk to students and say, what is biophotonics, I quite often take a laser pointer like this and say, what is happening? And that is biophotonics. So the question is, how do you see that, or how do you interpret that? And can you actually use that for medical purposes? So there is a large, I mean, the motivation for doing it easy, of course. And light is unique in that way. It's sterile, it's not invasive as we think, and you will see perhaps at the end that there might be thoughts about light even having other types of effects on the interaction with tissue. But what are the area that we span in biophotonics then? This is from University of Davis in California. So the biophotonics area actually goes from humans to large interpretations using quantum or photons down to the smallest things that we think, at least if we're talking about medicine, that is the DNA. So we have the full scale here where we can actually use biophotonics. So where is the focus today, which I think we're much focusing in? Of course, we have worked on humans, like large or macro scale, for quite a long time. And those methods are well known. They have been there for many years. We're slowly getting at smaller and smaller objects or fields of view. And I think a lot of what we're doing today is in the cell and tissue area. And of course, different sections of biophotonics is also doing it in the DNA region. So if one make a list of all the methods that you probably would realize that we're using for diagnostic purposes. I mean, X-ray, it's not new, it's quite old, but it's still in the part of, some would say, not biophotonics. But if we use the definition, I would say we're still using that as a part of biophotonics. Infrared imaging is something that we have used, are still using, and it's actually developing very much. Contrast microscopy, together with the ordinary microscopy, is of course also biophotonic. Can you use temperature as biophotonic? Actually, yes. Spectral imaging, you have fluorescent imaging, ballistic photon imaging, and optical coherence tomography, multiphoton, and I mean the list could be quite long about those that you're using. And of course, optoacoustic imaging is one that is perhaps, at least, well, let's call it hot topic on the market today, I would say. So we'll see a little bit what it will end up in at the end. On this more therapeutic side, we have also old methods like treating smallpox. One can do that with light. We can have oxygen radicals. I'm talking about PDT for instance, that we're using. We have some others, conversion of photon energy into mechanical energy, photocoagulation, which is also another area where biophotonics have a more therapeutic effect. And of course, as I mentioned, photodynamic therapy is quite used for a long time now. And photocoagulation and irradiation. What are the topics that we try to solve actually? What happened when you shine light on the tissue? If this is the slab of tissue that you actually see, and would like to see what is happening inside a very small, tiny, let's say, square or cubic millimeter, or let's say, if we take the nanoscale, even less. If you shine light, of course it depends on the type of light you're using. The light interaction process is a couple of things that will happen. It will be scattering, it will be absorption, might be, if you have internal sources or things like fluorophores, you can have fluorescence, of course, or some other processes. But mainly it appears like that. It will be transported through, it will be absorbed, it will be backscattered, it will be scattered in some directions, it will be diffuse reflected, and you will see that there is a large waste or majority of applications or methods that we're using diffuse reflectance. But we also have diffuse transmission, but the idea of solving those problems is sometimes a little bit more complicated. And that is, that is in terms of the distance the light can travel in tissue. So the question is, what is we actually seeing? I would say the main basic processes that you see, that is absorption, scattering, and fluorescence, but they are combined in some way, so you cannot perhaps isolate them. So you have to encounter them for all. If you apply that on tissue, for instance, that means that you have a model, or you have an area, field of view, that you are trying to discover the optical properties of the tissue, for instance. And how do you do that? What is your interpretation of the tissue? Because if we're working with material, we quite have ordinary structures. We have regular structures, or we know a little bit more about these objects that we're looking at. But tissue, if we go down to the scale of vessels or tissue or cells, may look like this. It may be the last or minute intricate network of, for instance, supporting vessels, capillaries, arterioles. Those are actually carrying or modifying the optical properties of the field of view that we're looking at. And it was, I mean, just 150 years ago that we actually discovered that, I would say, tissue would look like this, the porosities of flesh. I mean, we didn't know that blood came from the left ventricle to the right ventricle. We thought it was getting loose of somewhere in the left foot and just disappeared, which is not very true. So the microcirculation, which actually is the target for many medical applications, or where we actually use biophotonics, is quite an intriguous or very complex model. I think this image is, or sketch is actually appearing in all theses in biophotonics, more or less. At least the last 20 years I've seen it in almost anyone or everyone, and it shows you about the complexity. And try to, because now we're going to try to estimate the optical properties of this in some way and use it for diagnostics or preventive purposes. if we refine it a little bit, we make better sketches and say this is, for instance, the let's say the distal part of the arms or upper skin, and you will see that you have, for instance, capillary loops. That comes up here where you have the exchange of molecules like oxygen delivered to the cells in the breathing cycle. And this is, of course, of interest. And how could we monitor that and look by that by biophotonic methods? But the interesting is, of course, how could we estimate these optical properties in a way that we can make our diagnosis or prevention in medicine. And that is, of course, not so easy. So that's why the old methods, like microscopy, has been quite widely used in biophotonics, I would say. Because if you take a microscopic image, it looks like this. This is also the same, but this is actually the truth, we think. Biophotonic imaging. This is capillaries that are actually seen by a microscope. If you have a diseased tissue, it might look like this. So the question is, how would have that modify the optical properties? And how would you have sensed that with some other types of biophotonic method? This is, of course, the static or frozen eye movements, or what you see in the tissue if you take a snapshot. But if you go further on and look at this, this is actually the dynamic part of the biophotonics, how to monitor the optical properties of temporal changes. This is recorded from a mouse mesentery, and this was actually blood cells that you were seeing moving around. And you know that many biophotonic methods actually are using that property, velocity, to try to create some sort of perfusion values building on biophotonic methods. But if we still go back to the microscopy part, which is, I would say, where you started to ask what is the optical properties that you can see from these types of images. This is an epiluminant microscopy image, and what you see is actually the arcs of the capillary loops from tissue. And one can ask then, what is it for diagnostic value in just looking at a microscopic image like this? That is, of course, what's called, which was the Nobel Prize in 1930, that was the Krog cylinder. I mean, diffusion of oxygen between supporting vessels. So by just looking at the infrastructure here, or let's say the microstructure, you could probably make some diagnosis about, are there enough supporting vessels that could actually give you a living tissue or a viable tissue? Or do you have to enhance it in a way, or perhaps support it? That could be done by different microscopic methods, of course. You can have direct epilumination, but you can also have what's called the dark field or Sidestream dark field, where you actually use the property of diffusing light into the tissue to get, I mean, very complex network description of the tissue. You don't even have to look at the capillary arcs at that time. One thing that we did a couple of years ago was to try to see, could you use your mathematics applied on these types of biophotonic 2D dimension data sets? And we can, of course. So by looking at what we thought was some sort of model for the Krog cylinder, or how that works of diffusion distances in the tissue, you can actually model that and trying to locate all the feeding vessels and create some sort of network which will give you some sort of distribution if it's well nurtured or not. That has been used in sort of rare diseases where we have actually looked at that. Shining light then on the tissue, if we're talking about laser light, because this is, I would say, more coherent light than you use in microscopy, will create, if you focus, speckle. Speckle pattern carries information about the surface, so it's actually either destructive or constructive interference that you see. It of course depends on where you have your detector and how it looks like. But this tells you something about the surface. So that is some sort of static material. If you apply that on something diffusely, or which you see underneath, then you will have, for instance, skin tissue. You will see a speckle pattern that actually is moving. Why is it moving? It's because of the blood cells, because the blood cells now are moving, so you will actually have a different speckle pattern per time unit. So the idea is, of course, to encode or decode this speckle pattern into something useful for diagnostics. And that means perfusion. So how do you, for instance, evaluate or do that? And you can do that by a little bit different methods, either by doing a large waste of modeling and processing, of course, of the signal, and you get something called laser Doppler flowmetry, which I've been a part of for some years doing that. And the Doppler effect is well known, of course. That is the redshift. You can see that in many optical applications. But there is also redshift, which is related to blood flow. But the difference in magnitude is, of course, different, because the speed, the expansion of the universe is a bit faster than the expansion or the movement of the red blood cells, which is perhaps lower than 1 millimeter per second. But that is possible, and you can do that by some sort of heterodyne detection techniques. Of course, you want to do that in a spot, and you can do that. So that was what's called a laser Doppler flowmetry in one point. But you wanted to do that, of course, in imaging and do this spatial interpretation, because there are spatial differences. We saw from the microscopic images that the tissue is not homogeneous. It's definitely not homogeneous, it's heterogeneous. So you need to do that in 2D data sets. And the outcome can look like this. This is a pseudo-colored images of, for instance, it's actually my supervisor's hand. At one time, we put the soldering thing into his hand. It burned him a little bit, so he was screaming, but it doesn't matter now. Which means that you create wounds, and wounds also create a large inflow, because you start to heal the wounds immediately. After 2 hours, you get an inflammation process. So what you actually see is a large perfusion increase, which could be increased perhaps to 500 times or even more, because you're only using very few capillaries actually in normal tissue, about 10 to 15%. Another area where you have actually, and this is of course available today as a clinical tool, that is, you can do this is open heart surgery, where we are not doing, for instance, images, because this takes a little bit time to do that, the interpretation of those maps. But here we have a single point measurements that we can actually insert into the tissue and actually following in coronary replacement, how actually the heart is restoring after different types of settings for the heart. That is one way of doing it. But of course you want to see the temporal changes, because this will actually, if we have very good computers and for doing this, it will take us about 2 to 3 minutes. And you know that in 2 to 3 minutes a lot of things will happen. So the implementation that we're doing today is, of course, to do it with more laser speckle imaging, because you have the speckle, but there are ways of handling the speckle in a way which is actually related to the Doppler shift. And by doing that, you can actually create images, and this is from Port-Weinstein's treatment. And Port-Weinstein treatments during surgery in the clinic is very important to follow, that your procedure is very well done. And that can be done because this is actually real time now, instead of the 3 to 4 minutes that we can do before. But that means another interpretation of the Doppler shift using laser speckle imaging, but it also means actually lowering the resolution of the image, because we have to do subsampling in the image or in the data sets that are necessary for doing the interpretation. This is, of course, structure. This is, of course, perfusion, time variance. But mostly we're interested in the content, what is hidden behind there, or what is in there. I mean, a perfusion map doesn't tell you everything. So you need to look what is inside and what's modifying your optical properties. And if we take the waste majority or the most important parts that you find in there for diagnostic use is, of course, the things like hemoglobin and deoxygenized hemoglobin. That means how are the tissue living? How does it work? Does it function well or not? And there are, of course, other types of what we call chromophores intended in the tissue that we would like to look at. For instance, the melanin and the production of melanin after, for instance, sun tanning. Or dermatologists want to see what happens if you are allergic reactions. And of course, we have a large water content which is used for other types of biophotonic interventions. And one can see that actually Isaac Newton actually a very long time ago said, give me a prism and I will see the color of light, more or less in that sense. What are clinically useful today is, of course, spectroscopy in one way or the other. There are many types of spectroscopy one can use. And spectroscopy means trying to understand the content of the tissue in a way. And the thing that we're doing is, like before, introducing laser light or some broadband light on tissue and trying to interpret what are the spectroscopic signatures that we get and how do we interpret that. This is actually the spread of an injected pencil beam in a diffusely scattered media, and depends on, diffusely means, for instance, tissue. So that means you have the flux values of the energy here described in some way. The way we're doing it is often that we're sampling somewhere here on the reflectance, diffuse reflectance scale. But we know that it's very hard to collect what is the truth value in this sense and how to interpret that. So we have to come up with models. If we simulate this in Monte Carlo simulations, for instance, the way of interpreting photon interaction with tissue looks like this. It's quite messy. But this is actually what we later on will use as some sort of prediction for how this tissue, the optical properties, looks like. You can also see perhaps from this picture that what is the heterogeneity of this tissue? It's not very high. It's actually two slabs. It's one slab having one optical property and another one which is probably a vessel. So it's actually one layer model which is actually giving you some information that could be useful. What we're trying to learn is actually how to put what's called a banana model, trying to see from the injection place to the way where you sample in the diffuse reflectance map, how to interpret that. And from a previous study, and we have shown that if you have non-transparent, like for instance increased of melanin up here, you could see actually, this is a Monte Carlo simulation, how the fluence rate actually differs very much of what photons or energy actually reaches the target. So this is actually the fluence map. This was actually a non-transparent overlay that we put there to see how it works. The interest or the use of, let's say, point spectral methods are quite useful today, and we can use them clinically. But I think we're more going to what's called hyperspectral imaging, which means that we also increase the things we would like to look at. For instance, if we think about skin lesions, our main goal is, of course, to detect this. Here we can see it, but some skin lesions you don't see at all. They have the same color, but they are still not very nice to have. So sometimes we would like to have screen methods for detecting skin lesions. That means that we have to have spectroscopic methods that actually have the ability to do spectroscopic 2D data sets or hypercubes. And one technology which you often use here also is some sort of multispectral imaging. That means different bands of spectrum that you can use and do some interpretation of. Or you can do it by building up with some sort of technology with ordinary cameras and computer steering filters that you can use to actually create a good environment. Still a little bit slow, of course, but it's useful. And the result is actually that you will get hyperspectral cubes like this. So you have the spectrum in that direction, and you have the 2D dimension of the image in the other. The thing is, how do you interpret this into the optical properties and the physiological processes that is ongoing in the tissue? If you started with having one-point problem, now you have, if you have a VGA format or the lowest format you have for resolution, which is 640 by 480, you can sum that up, which gives you approximately 1 million pixels. And if you have a spectrum in every pixel and want to tell the optical property in that pixel, you need a good computer or a good model for doing that. But it's coming and it's getting better. We can do that, and we can almost do it today by using graphic programming units and CUDA language, and actually do it in a few seconds today, and that is good. So this is actually an image where we actually see the oxygenized image after not a sun tanning but a UV provocation. So this is actually a round UV provocation we have done, and you can see the skin around it, and this is very high perfused. That means that it has very high oxygenation. If you take a cross section of that, you can actually see the signature of the oxygenized blood, which is the two peaks that you see from the absorption spectrum. And it's outside there, in this point, you see the reverse, which is deoxygenized blood. Of course, quality control in this is very good to do if you should use it clinically. And this is actually the error map if you compare it. And you can actually see there is no errors. You can see there is a little bit whitening in the middle, but it's very low actually. But you see two black dots, but that is actually ink marks. They are non-physiological. So it seems to be working very good. And we had occurrence of good fit over 0.95% doing this type of decomposition of the hyperspectral cubes. We can also look at the melanin. This is a spot in an image which is actually melanin, and we can definitely say that because this is hair, and we know that hair actually contains melanin. So we have a reference in the image that says it was actually a melanin spot. So I think this was one of the first images on melanin that we were able to produce in this sense. Talking about putting the soldering target in the hand, what will happen, I mean, temporarily when you do this? And of course, after UV provocation, you know that after 72 hours you get brown because you have been sun tanning. But that means also that the inflammation in the tissue is actually that process, the physiology is actually changing very much. And this is actually the physiological process that you see the sun tanning first, or the UV provocation, that you can see that goes down it starts very quickly within the first day, and then slowly after 72 hours it has diminished quite a lot, and after 96 hours it's starting getting normal again. And I mean, it doesn't hurt so much anymore if you were sun tanning too much actually. So this is, I think now it's available. I mean, you can do 2D data sets with hyperspectral imaging, even I would say clinically. Of course, the equipment still are not so handy as we would like them to have, but they can actually be done within, I would say, a very short future. The other thing is that we're looking at some sort of 2D surface structure. But we are quite often interested in going deeper down to see what is happening in the tissue by the method. And the dominating, I would say, is optical coherence tomography. That is based on differences in backscattered light from tissue as we did before, but this using quite different light sources. It's not using coherent light sources, but low coherent light sources of light. And it can be used quite extensively. It's using the Michelson interferometric setup actually for doing this. And this part is probably very well known to you, but the light source is not a high coherent source, it's a low coherent source, which means that you can actually use it for detection of. This has been on for quite long, and today it's a clinical tool mainly in ophthalmology, or looking at the eyes, for instance, loosening of the retina, or diabetes patients coming to the clinic. And this is quite often images that you see, which is the retina, and if you have an edema, it's starting to loosen. But there is no, I would say, other methods possible to detect that small differences. Or there are very few anyway that can be comparable to OCT that can actually detect that in that area. The good thing with the target as the eye is, of course, the transparency of the eyeball, which means that you can actually reach the target. If you go, for instance, to other tissues, you can find images like this. For this is from a colon tissue. You can see this is the coherence, or sorry, the optical coherence tomography image, and this is actually the stain technique that we use. That is why it's called optical biopsy. So we can take biopsy, and this is of course very interesting when we start to talking about pathology. And you can see that they are actually coinciding very well, the images taken from the OCT and the biopsy. Hopefully they're coming from the... Of course, it has been on now for about 10 to 15 years, and it's available. It's available for the eye department, but it's also available today for dermatology. We're actually investing ourselves now in a a new type of OCT that we'll be using for brain investigations and also dermatology. But there are a type of new development like new light sources that can be useful, new types of speeding up the scanning, for instance, because the old A scan was very slow, and should you do 2D dimensional data sets, it created or took quite a long time. We can improve the depth of field for the imaging now. We can use also adaptive optics to increase the quality of the images, and also use polarization sensitive optical coherence to even get further down and even better structures of the tissue. Static images, you say, and of course it's static, but since it's coherent or low coherent light sources, you can actually use another thing that was a part of another technology that was used in biophotonics, and that was the Doppler shift. So that means if you actually look into what happens is if you have moving blood cells, you will actually have a change in the low coherence center frequency here now. Which means that if you're able by some sort of using a short Fourier transforms, you can actually detect the Doppler shift, and you can actually both get a transversal section or a two-dimensional section and superimposed on that temporal data, displaying the perfusion, for instance. And actually this was shown some time ago, but I wouldn't say it's until now it has been available clinically to do this. And this is actually one of the equipment that we're investing in right now, is to actually be able to do three-dimensional Doppler images with OCT. And this is actually just to show you that this is a cross-section, which is an ordinary A section of a OCT. And here you can see actually a vein and an artery, which is having some activity displayed by the Doppler shift. I think this is a really improvement that will take this technology, which is even nice today, but to even higher amplitudes, I would say. Could you then impose the third thing, that was content, of course, on this subject? Of course you can do that. So you can actually also do, or at least, perhaps not clinically yet, but it has been proven that you can do spectroscopic OCT imaging today, which is very neat. And what will happen is that you will get images like this, where the pseudocoloring now is actually displaying the difference, for instance, oxygenation maps on a cross-sectional basis. And you can actually find out where the oxygenation is actually residing. And if one look at some sort of success stories, it means that we have been able, or we haven't, others have been able to do this, of course, that we can actually do mammography in Massachusetts. We have been able to reconstruct 3D images of breasts, and we can do that with a good specificity of more than 88%, which is actually better than the techniques that we normally use for this type of investigation. Of course, I think a young biophotonic technique like OCT is just on its infancy. So it will actually come more. So actually, I think it was just a month ago that they say we will have handheld OCTs able to bring home, actually. And I found one when sitting down yesterday, and moving from the clinic to the home. This is actually veterinary. This is an unusual patient, I would say, that we can use OCT, it's actually an elephant having problem with his sight. He's a little bit old, so we had to do a little bit investigation on the elephant. But that was done by handheld microscopic, OCT that was brought up to the zoological or to the zoo. I think that was quite amazing. What is the technology that will follow OCT? I would say it's the technology that creates perhaps even better, because there is a problem with OCT and microscopy, laser Doppler flowmetry, SPECKLE imaging. What is the depth? If you would ask me 15, 20 years ago, what is the depth of your field of view, or what do you sense? I would say 1 millimeter, which we said, and we were of course wrong. It's a couple of path lengths, actually, we can see. But there are technologies able to actually go deeper into tissue, because I told you that diffusion optical tomography is hard to do because it will give you so very bad signal-to-noise ratio. That is, of course, photoacoustics. Because the trend is now to going into more like, say, multimodal imaging, of using different types or hybrid systems. And photoacoustics, I would say, is one of the first systems using hybrid. It consists of lasers and ultrasound. Both of them are able, in a way, to have making images. But this using an injection of laser light that creates a adiabatic process or expansion process because of the short pulse length, or just short pulse, which create a ultrasound pulse which can be detected, which is speckle free in a way. That means that you can also reach higher depth, up to the 5 to 6, perhaps 7 centimeters into the tissue, compared to OCT, which gives you about, let's say, 0.5 millimeter or 1 millimeter. So there is a waste difference in what we will see. So, but the thing is that you need a good absorber in the tissue, and a good absorber in tissue is, of course, blood. So that means that the first thing you will see is actually blood vessels. Looking at this. And this is actually, you see the SO2 is segmented venules and arterioles, and this is actually some way of displaying the total hemoglobin compared to some histology. This is actually images that I borrowed from Leon Wang, and what is able to do is actually to create three-dimensional images or maps of the vascular tree like this, where you can actually see the complete structure of it. And he likes rotating images. The one thing which could be very interesting, if you're going back to ideas about, for instance, melanoma detections. If you have an ingrowth of a melanoma here, for instance, it could be interesting to see if the melanoma has introduced it or interjected into the blood vessel or not. Because if it hasn't, it can be removed and you can spare the vascular tree. And if you look here, you can see now that the melanoma actually is outside the vascular tree and it can be removed. And there is very few other technologies that can actually give you these types of information. And of course, we can, since we're focusing on blood, we can also get images and temporal images of, for instance, going from hypoxia to thermoxia and hyperoxia, and how that looks. That is also very easy to do. And the thing which is very easy to do is take more time than is necessary, if I look at the watch. Prevention. I'll give you just a few slides, then I will stop actually. Photodynamic therapy is where we use light, for instance, to excite something that we have introduced to the body that can be used to actually kill cancerous cells. And this has been used for ALA5, for instance. We have introduced that, and we can use shine light on that. We can activate it. It will create lethal things that will actually kill the cells, and it will go away. So it's a therapy that is very useful. The problem is to find the photosynthesizers. And it has been debated how to use that, of course. But they can also be used in things like this, actually coagulating. So you can have other types of synthesizers that actually coagulate blood. It doesn't have to kill the environment. So that could also be used for coagulating instead of laser coagulating, for instance. And this is a hope that we will actually develop PDT. It can in some way be the future of cancer treatment. Something. But we don't know that yet. It depends on the photosynthesizers. Another thing which is a little bit similar to this is optogenetics, where we can also put in synthesizers actually to, for instance, to block nerves and to block other functions. We can actually switch it on off by shining light on that sensitizer. And I think that is a thing that one claim that this could be actually something you can do for making the blind to see. We will see, I would say. I'm not sure we will there yet, but it might be a thing that we can do. I think what we will see for the future now is what's called multimodal imaging in biophotonics. And I was supposed to give you a little bit of the research we're doing right now back home, but I skipped that because I think I've taken too much of your time. And just show you the last slide then, or the last two slides. That is what we will do back home right now to make this more clinically available. We will try to actually measure structure, content, and perfusion by putting up a hyperspectral imaging systems with some sort of SPECKLE imaging devices in the same unit and being able to look at it in the same field of view. And that means that we will probably, hopefully, will be able to grasp all the things that makes us a clinical available tool for us in the future. We're actually setting up that for the first time right now. But if one should say something, we're in the position of using light for probing, manipulating biological processes. That is what we're doing with unprecedented precision and control. And this can be achieved with the common capabilities of molecular techniques and optical technologies in our toolbox. We have a lot of things in our toolbox right now. Some of them are clinical, some is just on the edge of getting clinical useful. And this, of course, creates new possibilities and opportunities to generate fundamental information to solve some of the biological problems that we have. And I think, as I see it, biophotonics is, as I can say, the future. And I would say, you're welcome to take the ladder. Step into it.
Thank you. So maybe just shortly 1-2 questions. question. Which from these all techniques from biophotonics seems more perspective for you, or more interesting? Which field seems just starting developing, and I don't know, will have quite a lot of developments in quite close future?
Sorry,
which technique seems more perspective? I don't know, OCT.
The one that has the best opportunity now to develop, you think?
Yeah.
I think if we can solve some of the problem with photoacoustics, I think that is a technology that will give us something we very long has lingered for, and that is the depth sensitivity of the data sets or the tissue, because up to now we have mainly been in the range of millimeters. And if you compare that to the regular ones like X-ray, I mean the macro scales of imaging, where they are, I mean, transluminal imaging or whatever, and diffuse optical tomography is complicated. But with this hybrid technique, if we can solve, one of the problems is, of course, to get a good transducer for the detection of the ultrasound pulse. If we can do that and find there are some more glitches that we have to do, then we can actually reach the distance of, let's say, 6 to 7 centimeters down in the tissue, which is enormous compared to 1 millimeter. And we still have a very high resolution. Of course, it will create enormous data, which might be another problem. But I think it has the future. And what I've learned the last couple of months is there is a lot of a hush-hush about PAT or photoacoustics, because all the large microscopy companies are running the race of getting out the first clinical commercial system, because it's going to be a huge market. Okay. So that is what I think.
Okay, since we are out of time, but sure, thanks one more time for our lecture.
Okay. Thank you. Thank you very much.
And if somebody will have other question, I'm sure that professor will stay here for coffee time later. So just go and ask your question. The next presentation will be given by Dainis Jakovels, Latvian University, Atomic